Today we are going to talk about ionization energy under the unit periodic table. And my three learning goals for you guys is I want you to come to class being able to explain what ionization energy is. I want you to be able to describe the trend of ionization energy on the periodic table. And I want you to be able to explain why it requires more energy to take an electron off of the atom and why it takes more energy to take off each electron after that first one. And that may not make sense now, but after this lesson, you probably will find it easy. Okay, so first, all ionization energy is it's the amount of energy that it is required to take off an electron. So basically, to make an atom in a gas form, make it an ion. So from going from an atom to an ion, how much energy does that require? So for example, lithium, the lithium atom, get a periodic table, sorry. So for example, the lithium atom has 3 protons and 3 electrons. So if you were to take an electron out of the lithium atom, then you would have a lithium with a +1 charge and 1 electron. And the amount of energy required to take an electron from that, or to make it an ion, would be determined by the distance between the electron and the nucleus and its nuclear charge. So what that means is, sorry, sorry, I have my dog. If you want to see him, you can see him real quick. Hi, Fisticky. And he's not liking the fact that I'm giving you guys attention and not him. Anyways, so what that means is that the distance between electron and nucleus, so we have this, stop, Fisticky. We have this nucleus, okay? And then we have energy levels. I don't like this marker because it's not dark. We have energy levels. So let's say there's an electron and an electron, another electron. So the distance, the more energy levels that we have, okay, the more distance we have between the nucleus and the energy level, or the electron. Let's say there's an electron out here, and this is full. So the further the electron is from the nucleus, the easier it's going to be to take it away. Okay, and the nuclear charge. So remember, the nucleus is a positive charge, and so the more protons it has, the more protons the nucleus has, the more difficult it is going to be to take this out as well. Okay, that was okay. So moving on, we have trends. Okay, so again, every trend that we have, just like the very first lecture, as you go, the periodic table, as you go down, they all act the same. As you go to the right, they all have the same energy levels. So as you go down, so the group trend, so remember guys, this is a group. You're going to be so tired of hearing me say that. But as you go down the group, it's going to be easier to take away the electrons. So for example, you have fluorine. It's going to be easier to take away an electron from the chlorine compared to fluorine. All right, so looking at cesium and lithium, which is on the periodic table, lithium here and cesium all the way down here. So lithium here, cesium here. Cesium has 1, 2, 3, 4, 5, 6 energy levels compared to lithium that only has 2. So lithium has 2 energy levels around its nucleus and cesium has 6. And so the electrons in lithium are going to be closer to the nucleus. So it's going to be more difficult to pull that electron away from lithium than it is for cesium, because cesium, the electrons are further away from the nucleus. So you're going to get that shielding effect plus the distance, and it's just going to be, it's going to require less energy to take an electron off from there. Okay, so the periodic trend. So remember, periods are going across the periods. Okay, so that's the periodic trend going to the right. Sticky, please. Okay, so as you go across, it's going to be more difficult to pluck these electrons off, only because there's more protons as you go. So that pull is going to be stronger on those electrons, so it'll be harder to take it away. Okay, so let's just kind of stop here and draw a few things to kind of illustrate some of those concepts, because those are some pretty big concepts in just a couple of slides with a little definition. So I'd like to kind of cement these a little bit. So as you go, let's just take a couple of examples for group and a couple of examples for a period, just so you can kind of see. Let me straighten that out. Okay. So let's do, we saw the period trend, right, with lithium and cesium. Lithium had 3, so, and cesium had 6. So let's just draw it real quick. Lithium, here's the nucleus, had 3 electrons, so, and 2 energy levels, okay? I'm not going to draw all the electrons for cesium because that's a lot. So with lithium, this first electron that's going to be taken away is going to be a little more difficult because this is a positive charge, and the distance from the electron compared to the nucleus, it's very short, so this has a pretty good pull on it. Now with cesium, you have cesium, which is all the way 1, 2, 3, 4, 5, 6. It has 6 energy levels. So cesium, we're going to draw. I have really bad circle drawing skills. 3, 4, 5, 6. Okay, so we have 6 energy levels. That's so horrible. So the electron here, the distance is way further compared to lithium, where the lithium kind of stopped here. So it was a really strong pull from this positive nucleus to this electron. But an electron out here, that pull is not as strong. Plus, on top of the distance, you have all of these other electrons that are filling these energy levels. So you have a lot more electrons shielding this. So it's also kind of pushing that out. Okay, so it's easier to take an electron off of cesium compared to taking an electron off of lithium. That's the ionization energy, the energy it takes to make an ion. So that is a group trend. Let's look at a period trend real quick. Okay, so let's look at a couple of examples from the period. Let's look at sodium and then chlorine, okay? So they're going to have the same energy levels, okay? They're both going to have 1, 2, 3 energy levels. So we'll do sodium. I'm just going to make that its nucleus, and chlorine. This is the nucleus, okay? They both have 3 energy levels. So 1, 2, 3. Don't be confused. This is the nucleus. This is the nucleus. We'll do that. 1, 2, 3. Okay, so each of them has 3 energy levels, okay? But it actually gets more, here we go. It's more difficult as you go across the period to the right because you're increasing number of protons. So when you increase the number of protons, so for example, sodium, you can't really see that very well, but sodium is number 11, atomic number 11. And chlorine is atomic number 17. Okay, so that means, wow, okay. So that means this has 11 protons in it, and this one has 17 protons in the nucleus. So these 17 protons are going to really pull these electrons in towards itself compared to the only 11. So this pull is stronger compared to this one. Same amount of energy levels, but the pull from the nucleus, the nuclear charge, is stronger on the chlorine than it is the sodium. So that's why you have a different periodic trend. Okay? All right. So look at the what is it? The graph, okay? Look at the graph on the slide. The first ionization energy is for elements in the first 6 periods. So remember, periods are going across like this. If you'll look, what I want you to notice first is that lithium, you see at the very bottom in green, lithium, sodium, potassium, rubidium, and cesium. So those are all in this one, in this one group, okay? Remember from our first lecture or our first lesson, that elements in the same group, they will react similarly, okay? They have similar properties. So if you'll notice, they're all similarly easy. They have low ionization energies for their first, IE, whatever. So I want you to just keep that in mind. And if you look at the top, helium, neon, argon, krypton, and xenon. So you'll see that those are noble gases. So they're also down a group and they're acting similarly. I just wanted you guys to see your first graphic representation of groups acting similarly. They all are very difficult to pull the electron, the first electron off. And if you think about it, it makes sense, right? These guys are very stable and they're not going to want that electron taken away. Then these, if you'll look, I think I just drew one. Hold on, let me see. Did I draw lithium? Yeah. So if you look at lithium, okay, lithium has 1 electron on that outer shell, and that's not very stable. So it's going to be happy to give this one up, so it will have a full energy level here on the first energy level. So it's not going to require as much energy, and that's the same for sodium, it's the same for potassium, all of those on group 1, they all act similar. So just keep that in mind when you see these. That's why the noble gases take a lot of energy to pull that first electron off, and all of group 1, not so much energy. Okay. Now, it always requires more energy to remove a second or third electron. Let me kind of explain why. Okay, so let's take a look at this statement. So the reason why, so we're saying that we have, I don't know, let's pick magnesium, okay? So we have magnesium, and we'll draw its nucleus. Magnesium is atomic number 12. Let's do beryllium so I don't have to draw 12 protons. So we're going to do beryllium. Beryllium is atomic number 4. So we have 4 protons with beryllium. Okay. Now, I'm sorry, I want to put something in it so I don't write on the desk. I'm sorry, I'm not the best video lecturer. Again, I know I've told you that. Beryllium also has the atomic mass of rounded to 9. So we have 4, and we need 5 neutrons. So that's beryllium's nucleus, and then it has 4 protons if it's neutral, okay? So one energy level will have 1, 2 electrons, and then we have 3, 4 electrons. So we're told this is beryllium, and this is kind of the neutral atom represented in the planetary model. So we have that, and it says it requires more energy to remove a second or third electron because they're more attracted to a positive ion. So let's say we remove 1 electron, okay? So now we have beryllium. Okay, this is going to be lame, I know, but we have beryllium with the electron here. Okay, all right? And I'll go ahead and finish drawing. So there's beryllium, and we've removed the electron. So now we have, so that equals beryllium with a +1 charge if we've taken away 1 electron, because we have 4 positive charges and now we only have 3 negative charges. Okay, so let's say we take away, now we have a positive charge. So this is the charge ratio is off now. That means this nucleus is now more positively charged compared to that electron cloud than it was in the neutral atom. So now these guys are even more attracted to that center, that nuclear charge. So taking off this second one is going to require even more energy. So let's pretend we removed the second one. I know, guys, don't laugh at me. Okay, let's pretend we moved that second one. So now it is no longer beryllium +1. I should have maybe prepared this. It is now beryllium +2. Okay? So now it's beryllium +2. Let's remove this side. Okay. All right? So we have beryllium +2. And now you'll notice that there's actually no electrons in that outer shell. However, this inner shell is stable. So you're going to see a new word in the slide coming up, and that word is called isoelectronic. All that means is same number of electrons. That's all it means. Don't be confused by any of these words in chemistry. They all have very simple definitions. Okay, so isoelectronic just means same number of electrons. So now, if you'll notice, beryllium +2, the ion beryllium +2, is isoelectronic with something, okay? So if we only have 2 electrons, okay, we're going to look and see what it's isoelectronic with. So the only thing that has 2 electrons, other than beryllium +2, would be helium. Helium has 2 electrons, okay? So helium, so that means beryllium with the +2 charge is actually isoelectronic with helium, the noble gas helium. So it's stable, it's very stable. So if we were to try to pluck this off, if we were to try to pluck that electron off, that would require some serious energy, okay? That would require a lot of energy to pull that electron off, and simply because it would be like a noble gas, and so it would take a lot of energy like noble gases do to take electrons off, okay? So that's basically what it's saying, the amount of energy required to pull the second or third energy off. That's because this becomes more positive, and so the electrons are even more attracted to the center. No, sir. Okay, so when you hear these words, this is more of a vocabulary type slide, first, second, and third ionization energy. All that means is that's the energy required to pull the first, second, and third electron off. So basically when we had just this one, okay, and we just pulled this one off and it became Be +1, okay, that's the first ionization energy. This would have been the second ionization energy, and then this would have been the third ionization energy, would be E +3, okay? So that's all those words mean, is how much energy required to take off first, second, and third electrons. And then I am finishing off this lesson with some of the, some actual examples of ionization energies. If you'll look, sodium, actually let me get this, a clean one for you. So sodium, you'll see has the first ionization energy is 495.9 kilojoules. That's the amount of energy it takes, the heat, that's heat. If you haven't learned it in physics, you'll hear it a lot in my class. But kilojoules is just a form of heat, a measurement of heat, and energy, sorry, which is We'll talk about that being the same thing later. But anyways, so it takes that much energy to pull off an electron and make sodium an ion. So it doesn't take that much energy. And if you'll look here, you'll see sodium. Sodium, if you take off an electron, it's going to actually become like neon. So it's going to like that. It's not going to require a ton of energy. And if you'll see the second ionization energy, to pluck an electron from from sodium when it's isoelectronic with neon, that's going to take a ton of energy. Look how much more energy it takes to take off that second electron. So you have sodium, you take off that first electron, it becomes isoelectronic with neon. So it didn't take that much energy. However, if you look at the second ionization energy, it'll become isoelectronic with with fluorine, which is actually more unstable than neon. So it takes much more energy to become unstable than it did. Okay, moving on. Magnesium does the same thing, except its big jump is the third ionization energy. So if you'll see magnesium here, okay? Magnesium, if you take one electron off, it becomes isoelectronic with sodium. So it takes a little more, it takes some energy to come off, but not necessarily as much as it did with sodium when you took off the electron when it was isoelectronic with neon. So we have, now it's isoelectronic with sodium, so we take another electron off, okay, and it becomes like neon, okay? So that's why it didn't make a huge jump from 738 kilojoules to 1400 kilojoules. That's not that big of a jump. However, that third ionization energy, so we took the first ionization energy, it's like sodium. Second ionization energy, it's like neon. That's like nice. That's nice. It's stable. It has all of its energy levels full. It doesn't have extra electrons. It doesn't need any electrons. It's stable. Then you take that third electron off, the third ionization energy, and look how much energy it takes. It takes almost 8,000 kilojoules just to pluck an electron from its neon configuration to fluorine isoelectronic configuration. So what that means is just the first ionization energy, you're taking an electron away, okay? Second ionization energy, you're going to take the second electron away. And whatever electron it takes away, just go to the left, okay? If it's here, just go up and to the nearest noble gas. All right, guys, again, you kind of know the pattern. You know there's going to be a pre-class quiz. It's going to be 2 to 3 questions, and I'll go ahead and put the bullet points up for you if it's not up on your screen already. Make sure you know those going into class.